Wonderful. So I hope that is a little bit clearer to you guys. Definitely a lot of practice on figuring out the conjugate acid and base of different species. It's also important for you to go over this page and look at the differences between the Arrhenius and Bronson Laurie. And this page definitely tells you how Bronson and Laurie expanded the definition of an acid. Okay, so this is just again something as a rehash. We call substances that can either act as an acid or a base amphiprotic acids. Water was an example shown earlier where it can either act as a base provided that there's another acid present in there that can supply the proton, or it could either act as an acid if you add a base into the solution. So it has the capability of donating or losing its proton to the base. Okay, so water is amphiprotic. Amphi because it can go both ways, like your amphibians can go both land and water. Protic because it can either lose or accept your proton. All right. So the HCl acid that we have commonly seen can only donate one proton because this is a monoprotic acid, meaning to say it can only supply one proton. But there are other acids that can supply two or more protons. It has that capability of supplying more. So here are some examples. You have your carbonic acid. It can supply two hydrogen ions, and your phosphoric acid, which can supply three hydrogen ions into the solution. Now, contrast to what we learned, because this is not new to you guys. We have talked about how to name or write the formula of carbonic acid. So we said that there's two hydrogen ions in order to counter a single carbonate ion which has a charge of 2 minus, right? Um, Now, contrary to our beliefs or what we learned so far, it's not just that when you put this in water, it will dissociate two protons automatically into the solution. That is not the case. The way acids work is that they will distribute or give away their proton one proton at a time. So it's not just one go. Okay, so it's a slow release of protons. And so for diprotic acids, you can actually see it giving off its proton in two steps, as you can see in this whole equation right here. So the first proton is given off to the first water molecule, hence will give this carbonic acid one hydrogen ion less. So this is your bicarbonate ion or your hydrogen carbonate ion. Now this guy, the intermediate product, will further give off its last proton, so its second proton, to another water molecule, hence give you the resulting product carbonate ion. Okay, so there's a missing 2 minus charge there. Okay, same holds true for your triprotic acid, phosphoric acid. It's going to dissociate in 3 steps. This is the first dissociation with the first hydrogen ion to the first water molecule in order to form dihydrogen phosphate ion. Then this dihydrogen phosphate ion will then release its second hydrogen ion to water in order to form a second intermediate product called hydrogen phosphate ion, which will then release the third or the last hydrogen proton to the third water molecule. Okay, as a result, it will form a phosphate ion. And there you go. It's a step-by-step process. It doesn't get released in one go. So here's a follow-up question for you. Say, for instance, I have 1 molar solution of HCl in one beaker, and in another beaker having the same volume, and let's just say for the purpose of example, let's just say this is a 1 liter solution. Both are 1 liter solutions. I also have another acid whose concentration is the same. So it's also 1 molar phosphoric acid. Okay, so remember the concentration means the amount of HCl present in your solution. And so if you have 1 moles, that means for every 1 liter solution, it will have 1 mole of your acid HCl. So if you have a 1 liter solution, then in here you'll have 1 moles of HCl, 1 mole floating in the solution. And if you have phosphoric acid in this beaker, you also have 1 mole of the acid, phosphoric acid. Okay. All right. So now the question is this. Since phosphoric acid is triprotic and HCl is monoprotic, does that imply or does that mean that phosphoric acid is more acidic than HCl? So the question would be pretty much which of the 2 acids is more acidic? Is it A or is it B, the solution that has phosphoric acid? I'll give you a moment, hit pause for a bit in order to think this out. But the answer actually is no. It doesn't imply that because you have 3 protons in you does not mean or does not imply that you are more acidic than an acid that only has 1 proton or is monoprotic acid. So think of this as comparing 2 different guys. Okay, so you have guy 1, pretty average, and you have guy B who is triple his size. And now the question would be, do you think guy B can lift certain amount of weight more than guy A, who's the average normal guy? Okay, doesn't necessarily mean that's the case. Your weight doesn't imply that you can actually carry, or it's possible, but it's not a guarantee. Because guy A, even if his average sized, it's possible that he may be lean or full of muscles and he may be trained enough and has gone to the gym all the time, whereas B is not fit in order to carry the certain weight you want him to carry. Okay, so it's not the guarantee that B, because of his size, can carry more weight than your A. So how can we tell which acid is then more acidic? That's the good question. Okay, how can you tell which acids are acidic, or who is stronger acid than the other? Or another way of phrasing is that is, how can you tell which one is stronger or has a higher strength than the other? The answer has to go in figuring out the strength of an acid, and it is a property or the ability of the acid. There's really no way to figure that out. It is individual. It depends on the acid. And so it's really funny how we started in this class to generalize everything. We categorize them according to their families, and we have predicted their trends, and then eventually we learn to appreciate the individuality of each of these compounds. So what is the strength then? There's acids that are strong acids, and there's also acids that are weak acids. So what makes an acid strong and what makes the acid weak? Well, to answer that, the strength of the acid, or the capability of making, what makes the acid acidic or very, very sour or very, very corrosive, is mainly in its ability to give that proton into the water. Okay, its ability to release that proton into the water. So the one that we're looking at is really the amount of hydronium ions present in the solution. If you're going to have more hydronium ions, then that means that your acid is acidic. It can corrode a lot of stuff, it can react to a lot of stuff, so on and so forth. Just because a triprotic has 3 protons in it doesn't necessarily mean that it's going to release all of those 3 protons into the solution. It's not a guarantee. Okay, so for strong acids, like your HCl, hydrochloric acid, it is really special because the moment you put it in water, it completely breaks apart and dissociates itself. So it becomes ionized. So if you have HCl, when you transfer that proton, water becomes hydronium ion, and HCl is now reduced or simplified into its chloride form. Okay, that's your conjugate base. Now, in other textbook, it's actually simplified. It's written out this way. So you have HCl, and instead of putting water as a reactant, it's just placed as AQ, which implies that your HCl is in water, and that means that your acid breaks apart into its ions. So it's going to completely dissociate itself into its ion form. And it's also indicated by a single arrow. And so writing it out this way or this way is actually correct. But it's better to train ourselves to write it in a more correct manner, because in this first method, you can really see who is the giver and who is the acceptor, or where did the proton go, okay? So think of hydronium ion as a synonymous to hydrogen ion. It's just hydrogen ion attached to a water molecule. That's all hydronium ion is. Okay, now that's a strong acid. You put it in water, boom, it breaks apart. Okay, kind of gets like a broken Lego set. Now for weak acid, that's not the case. I mean, it is, but not really. So I'll explain more. Okay, so weak acid, for instance, HF, when you put it in water, there's really a proton transfer happening. It breaks apart into hydronium ions and fluoride ions. However, notice this double arrow. It indicates that this reaction is actually reversible, meaning to say the moment you break them apart into pieces, some of it will recombine back to form its HF counterpart, okay, the compound form. It's going to break, reform, break, reform in water. It's going to go back and forth until it will reach an equilibrium, and until there will be some that stays broken and some that stays intact. And so here's an example so that you can really see much clearer. So say I'm going to drop 100 molecules of HCl. HCl is a strong acid. I drop it in water. What's going to happen over time is that 100 molecules has completely dissociated into its ion form. So 100 hydrogen ions and 100 chloride ions can be found in the solution. You won't see a full HCl molecule in your water. It's going to stay in its ion form. Okay, that's what a strong acid is. Okay, notice there's a lot of hydrogen ions. That's an indication that that makes the solution, or actually that's actually what makes the solution acidic. All right, contrast that to a weak acid, hydrofluoric acid. If I have 100 molecules of HF drop into my water, okay, so they will break apart, recombine, break apart, recombine until it will reach equilibrium, such that only 3 out of the 100 molecules will stay broken into its hydrogen ions and fluoride ions, while the remaining 97 molecules stay intact in its compound form. So notice that there's only 3 hydrogen ions. They started the same amount. You started with 100 molecules, right? Nothing, the amount of water is still the same. You didn't do anything. It's just the characteristics of these acids. If you drop a strong acid, boom, it's going to give you exactly how much molecules you drop. So 100 molecules of HCl will give you 100 H plus ions. However, for HF, if you're going to drop 100 molecules of HF, it will only give you 3 hydrogen ions. So the acidity of HF is actually relatively weak, even if you gave or you placed the same amount into your water. Isn't that interesting? Why is that the case? It's going to be explained later, but I'm just going to maybe explain it to you in a more simple manner without even opening a can of worms, okay? Why is that the case? Okay, when the HCl breaks apart into H plus and chloride, they actually prefer it that way because chloride has less affinity to hydrogen ions. They don't like each other. They're fine, broken, and separated. Whereas for HF, the affinity of fluoride to hydrogen, in a way, it has something to do with its electronegativity too. Okay, let's see if I can write over this. So if I have HF broken into its ions, fluoride actually, or hydrogen ion actually has higher affinity to fluoride. So it would rather stay and get stuck with fluoride in order to form HF. And so there might be some that still stay separated, but majority of them will stay in its compound form. So that's really interesting. That's what they noticed back in the day, and that's how they categorize that actually some acids are strong, some acids are weak. And so which of the acids are weak acids? Okay, well, you don't have to worry about that. It's all already figured out. They have done numerous experiments and they narrowed it down to the strong acids. Okay, so they noticed that there's pretty much limited amount of strong acids. There's 6 here listed, but technically there's 7 strong acids. And the rest of the acids pretty much are weak acids. Okay, so here's a list of the strong acids. I encourage you guys during the exam to put this next to you or somewhere visible so that it's a good reference. But I like to put that, if you're going to take higher chem, I like to put that in look at these strong acids in the location of the periodic table because it's easier for you to memorize. So the first 3 acids are actually found in the halogen group. So you have your HCl, HBr, HI. In group 5A, we have the group version, the nitric acid, group 6A, the sulfuric acid, and the group versions of your chlorine. So we have perchloric acid and chloric acid. So that's a total of 7. I think it's easier to remember those strong acids that way. Okay. All right. Now, some of you might ask, or I probably am going to instigate it now. You probably haven't thought of this, but how did I know that for HF, only 3 of those molecules broke apart? Like, did I just make this number up? No, I actually did not. It came from a certain table. We're going to get there. But these numbers are actually well calculated and well known. Okay. So if we have a strong acids and strong base, then I'm sorry, if we have a strong acids and weak acids, and there's also the counterpart, the base. There's definitely a strong base and a weak base. Strong base, same with the explanation of a strong acid, is that these are compounds that when you drop it in water, it will break apart into its ionized form. So you're going to see a lot of hydroxide there. Hydroxide is the one that makes it acidic. Okay, weak acids are ones wherein it actually goes back and forth, and not all of them will completely ionize. So if you notice for strong base, this arrow, reversible arrow, or the reverse direction, is really small compared to the forward direction. It's very easy to remember strong base because there usually are hydroxides in group 1A and group 2A. So group 2A, as long as there's like group 1A, lithium hydroxide, sodium hydroxide, potassium hydroxide, these are categories of strong bases. And some selected few of group 2 metals. So strontium, calcium, barium hydroxides are usually strong base. So Cassarba, I like to remember that. Okay. Weak base, just like your weak acids, they have double arrow, so they do go back and forth in the solution. So now I have been holding some examples when we were doing net ionic equation in our double displacement reaction. I tried not to give that to you ahead of time because then you're going to get confused. But when we're dealing with reactions that involve with weak acids and weak base, although they have a state symbol AQ, because all acids and base have a state symbol AQ, it doesn't necessarily mean you're going to break them apart into ions. And let me try to find an example so that you can see. Okay, here's the magic of online. So I basically was able to find some examples for you. So these two reactants are an example of strong acid and strong base. You can predict the products using double displacement reaction. And if you notice, everything cancels out because HCl is aqueous and NaOH is aqueous. It breaks apart into its ion forms. And in ACl, if you look at your solubility rule, it's also soluble to water. So it breaks apart into its ions, right? So everything cancels out, and what is remained in the total ionic equation becomes the net ionic equation. Okay, so for strong acids, strong base, by definition, it can completely dissociate into ions, and so you can see them in its ionized form when you write it in water. Now, I'll give you an example shortly wherein you have a weak acid instead, and then take a look at the ionic equation. Okay, so here's an example of a weak acid reacting with a strong base. So you have hydrofluoric acid reacting with NaOH. Again, you can predict the products using the double displacement reaction. The product water has liquid state symbol, whereas sodium fluoride, because its compound contains group 1A, then it's also soluble to water. Now, for a strong base, we know strong base dissociates completely into ions. We can see that it's being broken apart in its ion form. Water, because it's liquid, it stays the same, and the product NaF also gets broken apart. But if you notice, HF, which has a state symbol AQ, did not get dissociated into water. And so for weak acids, when you're asked to write the total ionic equation, even if you have the state symbol as AQ, you do not break that apart into ions, because remember, it's not a guarantee that it will dissociate completely into ions. The same holds true for weak base. If you have ammonia in there, you can't break it apart into ions. I hope that makes sense. And so if you write the net ionic equation, we cancel the ions that can be found on both sides of the equation, leaving you with this as your final equation, the net ionic equation. So that's what's happening for net ionic equation of weak acids or weak base. You're going to see those entities stay intact because by definition, a majority of these molecules will stay or remain as a compound in water and does not dissociate in water. Okay, so then we'll have an example again. We have here our sodium hydroxide If I drop 100 molecules of sodium hydroxide in water, it will break apart into 100 molecules of sodium ions and 100 molecules of hydroxide ion. And the more hydroxide there are in the water, the more it gets really, really basic. So you have that alkaline property. Whereas if you have ammonia, if you try to bubble that gas in water, if you have 100 molecules of ammonia, only 3 of them breaks apart into ammonium ion and hydroxide ion, while the remaining 97 stays as ammonia. Okay, so that's why it gives off the release of only 3 hydroxide ions. Even if you have the capability of giving 100, but you only dissociate 3, that makes it a weak base. And so now the question is, okay, so how did you get those numbers? How can you tell that there's only 3 out of those 100 have broken apart? This is done by experimental method, and we can calculate that by looking at the ionization constant for acids and base. And if you quickly Google up the values of the ionization constant, you can easily search them up online. Okay, so these are acids ranked according to their acidity, and also there's also base Kb values for base, and it ranks the strength of the base. Okay, so what do these values, these nominal values mean? This is actually from an equation um, taken, or concentrations that's found in water. So kind of like this. Ammonia, after leaving 100 molecules of ammonia in water over time, it's going to reach equilibrium. And then they measured basically the amounts of these concentrations in water, and they compare that to the initial amount of the base that they added in. Okay, so this is the equation that they derive this number from. Okay, so Ka is actually, to write the equilibrium expression, all you need to do is take the concentrations of these species, or the concentrations of the products, multiply them together, and then divide it with the concentration of the reactants. Okay, so you have the acid ions, so H hydronium ion, times the amount of A ion involved there in the solution, divided by the initial concentration, the concentration of the HA in that solution. So that's your Ka value. So notice that for HCl, for instance, so if you drop 100 molecules of HCl, say in or let's just make it simple, okay? So these square brackets imply the concentrations in terms of molarity. So the units would be 1 moles per liter. And so to make this simple for us, guys, so let's just assume we've dropped 100 moles of HCl in 1 liter solution. So you're going to get 100 moles of hydronium ion and 100 moles of chloride ion. So if we write the Ka, or calculate the Ka value for HCl, that would be 100 moles per liter, or molarity, times the concentration of your chloride, which is also 100 moles per 1 liter solution, divided by the concentration of HA in, or the acid in the solution. Remember, when you drop 100 molecules of HCl, all of them had turned into ions. There's no HCl as a compound present in the solution. So this right here is not present, okay? So we can just say 0. So the values of that A big number divided by 0 is always a relatively high number, as indicated by infinity sign, right? It's a really, really large number, something that we can't measure. Now, if we take a look at your HF, you have 100 molecules, only 3 of them becomes their ion form. The remaining stays intact, HF. So if we write the Ka number for HF, it will be 3 moles per liter times 3 moles of liter fluoride ions divided by 97 moles per liter. Okay, so that's pretty much a number right there. Okay, so that's the value pretty much for your Ka value. So notice that you have 9 in the numerator, and the denominator is still relatively high. So what do you expect the Ka value will be? The Ka value is actually relatively small in magnitude, okay? This may not be the actual because I just rounded off the numbers, but it would pretty much go close to this value right here, okay? So the more products you have in this equation, in the solution, the more this number goes up. And so the magnitude of your Ka increases, and that implies that your acid is a lot stronger. It's very, very corrosive, right? Because it has dissociated majority of its ions into the water. Okay, so we're not going to get into the calculation. What I want you to know, or what I want from you or expect from you, is to know how to write the equilibrium expression of the equation, or if for the reversible equation. So say for instance for this, the first problem, the Ka is equals to, remember, it's always products divided by the reactants, okay, raised to their coefficient. So it would be hydronium ion concentration, write it in square brackets, multiplied by the concentration of your chloride. So square brackets imply concentration, or the amount in molarity, raised to the power of their coefficient. So that's power of 1. You don't have to write 1 in here, but just know that if the coefficient here is more than 1, then you have to change the coefficient up there, divided by the concentrations of the reactants. And in this case, it's the concentration of your HCl raised to the power of 1. Now, why did we not add water in here? That's because water has a state symbol liquid, L. We only put compounds or species that has AQ or gas as their state symbols. So don't include liquid or AQ, liquid or solid state symbols. Okay, so if they're solid, do not put that in the equilibrium expression. Okay, so let's try to check our knowledge. Let's try to calculate the equilibrium acid ionization expression. So write the equilibrium expression, or the what we call as the acid ionization expression, the Ka value of this acid. Products multiplied by the other product divided by the reactant, HC2H3O2. Okay, there you go. Okay, so what I have here is a list of several acids and their Ka values. So notice that the exponents is always a negative because it's close to 0. And the bigger the negative value is, the more it's really, really close to 0, right? So this, if I write this in the ordinary displays, it becomes 0.0075, moving the decimal place to 3 times to the left. This is 0.00068. So notice that if you have 13, then you're going to move the decimal place 13 times over to the left. So it's really, really close to 0, right? So The smaller this number is, that means the weaker the acid gets. Okay, so if you're going to rank them according to their acidity, then you can say that vinegar is then more acidic than your soda, your carbonic acid found in your soda. Okay, so it's listed according to strength or ranked according to strength, where this is the strongest in the list, and down here is the weakest. Okay, acid. Now, that's kind of faulty to say strongest, but relatively strong compared to the acids that's on this list. Because we can't really say that phosphoric acid, again, is the strongest acid, because that is not on the top 7 list of strong acids. Okay, so maybe I should say it's the strongest weak acid. How about that? And this is the weakest of all the weak acid. Okay. Now, in the last column, you will see percent ionization. You can see that it's by percentage. So this is actually derived from Ka, and we're not going to get to the calculation because this is beyond your scope of learning. But what I want to show you here is the percent ionization and what that means. So it means that if you drop 100 phosphoric acid molecules in there, roughly 8.3 molecules have ionized, while the remaining 91.7 or 92 molecules remained intact. And so if you look at your hydrofluoric acid, that's where I got the 3, the value of 3. That's where it came from the percent ionization. So it just gives me a rough idea of how many molecules have ionized and how many has remained intact. So notice acetic acid. Acetic acid has an ionization value of 0.42%. That means that if you drop 10,000 acetic acid molecules in water, only 42 of those break apart into ions. 42 out of the 10,000. Imagine spending $42 out of your 10,000. You're still 1,000 rich. It doesn't really have that impact, right? So it feels like your acid did not completely ionize. It did not dissociate into H ions. H ions is what makes the solution corrosive, not the acid. Because even if you have packed with lots of protons in you, but if your ability to release that is limited, just like these acids, then it's not going to have that corrosive capability or that acidic capability. Doesn't mean that it's not gonna burn, because pure acetic acid can actually still burn, but relatively one can really eat away a metal quickly. One will take like how many days to do so. Okay, so counter to the acid ionization constant, the Ka value, we also have a number for the base. And the same thing holds true. The bigger the number, that means the stronger is the base. Okay, so if I'm going to ask you, okay, given this hypothetical equation, write the Kb expression for this base dissociation equation. Okay, so again, it's always products and their concentration divided by the reactants, and disregard the liquid and solid species in the equation. Okay, so for this ammonia, Kb is ammonium ion times hydroxide ion divided by ammonia gas. I'll still put it because it's still gas, okay? So careful with this, guys, because if you just roughly go over this quickly and you will forget that ions have charges, you're going to get some points deducted. Okay, so salts, the products of the acid-base reaction. For ionic compounds containing metal or polyatomic ion, they're usually the cations, or the one that has a positive charge, and any nonmetal in that ionic compound or polyatomic ion anion, they're usually the negative charge. So NaCl, salt, we know it's a metal. Metals has positive charge. Non-metals have negative charge. Anything containing hydroxides are bases, and rather than being categorized as a salt. So NaOH, you don't categorize it as an ionic salt, but rather it's going to be categorized as a base. Now, common soluble salts as listed in the solubility rules will completely dissociate into ions in solutions. Salts are the products of neutralization reaction, as we have seen in the previous example. Okay, so you might be asked in this test to still predict the neutralization reaction, and you may be asked also to write the total ionic and net ionic for that reaction. Okay, let's try to do this for sulfuric acid. And as that TikTok guy who likes to cook, he will say, let's go. Okay, let's go. So sulfuric acid, H2SO4, reacting with sodium hydroxide. What is the product of this reaction? So we have our hydrogen ion. So always figure out the ions involved in this compound. And like any double displacement, combine the outer ions and combine the inner ions to form the product. So outer ions first, it will form water. Inner ions, sodium ion and sulfate ion. You're going to need 2 sodium ion to counter a single sulfate ion that has a charge of 2 minus to form Na2SO4. So that's sodium sulfate. By looking at the solubility rule, we figure out that any group 1A compounds are soluble to water. The state symbol for water is liquid. This is a strong base, so you have AQ. This is also a strong acid, so it is AQ. Okay, so is it balanced? No. You have to adjust the coefficient in order to have the same number of atoms on both sides of the equation. So now, is it balanced? Yes. Now I would say yes. Okay. So now let's try to write the net ionic and the total ionic and the net ionic equation. Total ionic, break it apart. So H2SO4. Whoops, what did I do there? Break it apart into ions. There are 2 hydrogen ions, 1 sulfate ion, 2, it kind of just gets distributed, sodium ion, 2 hydroxide ions to form 2 water, and 2 sodium ion, and 1 sulfate ion. Okay, cancel everything that's found on both sides of the equation. And what you are left, that would be your net ionic. Okay, Nie is 2 hydrogen ions plus 2 hydroxide ion will form 2 water. So notice that, as mentioned in the previous discussion, for net ionic equations for neutral acid, strong base neutralization, it's not always a 1:1 ratio, but actually you can simplify this because they all have the coefficient 2. And so you can divide this into 2 and it will be simplified into H plus OH to form water. I actually take that back. You can actually simplify that. Okay, so that's your net ionic equation for a strong acid and strong base. Okay. Let me clean this out so that I'll show the next problem. The nitric acid and potassium hydroxide. Nitric acid, HNO3 plus potassium hydroxide. Predict the products. I will have potassium nitrate and water. Now write the total ionic equation. You have H ion, the nitrate ion in the acid, the potassium ion in the base, hydroxide to form potassium ion, nitrate ion, and keep the water as is because it's liquid. Now cancel all that can be canceled out. And so what you're left is just, again, hydrogen plus hydroxide to form water, liquid. Okay, hydrogen and hydroxide, they're ions in water. So you have to put AQ as a state symbol. Okay, I chose hydrocarbonic acid for a change, reacting with a strong base. So we have HCN reacting with NaOH. Predict the products. Remember, it comes with hydrogen and a polyatomic ion cyanide reacting with sodium and hydroxide ions. So the outer ions combine to form water. Inner ions combine to form sodium cyanide. Sodium cyanide is soluble to water, and water is a liquid, has a state symbol liquid. Okay, so if we're asked to write the total ionic equation, be very careful now, because not all acids, even if it has an AQ, will completely dissociate to water. And remember, there's only 7 acids that can break apart into ions. And so for hydrocyanic acid, you don't break that apart. It will stay in its compound group form because it is a weak acid. Base also, you have to analyze. Not all bases breaks apart into ions. Now, any group 1A and group 2A, they're safe. You can break them apart because they are strong bases. And so strong base, by definition, they dissociate itself to water. So that's the reason why I kind of hold off in writing or using weak acids and weak base in the double displacement, or when we're doing that total ionic, net ionic chapter. Okay, so NIE, cancel both ions that can be found on both sides of the equation. You're going to end up with the compound acid in its compound form to form water and cyanide ion. Here you go.